In this last part of the quadratic functions lesson, we're going to be writing the equation of a quadratic function just from the graph. So if I can find the vertex, we want to start there. If we aren't able to find the vertex, then maybe we can find some other key pieces. In this first graph, we are able to identify where the vertex is. Our vertex is at -2, -8. So at least we know we could put this into vertex form using that vertex. Our vertex form equation was y equals a x minus h squared plus k. So we know how the vertex shifted. It shifted left 2 and down 8. We're going to at least fill in what we can. So that makes that x plus 2 squared minus 8. The only part we don't know is the a part of this vertex form. We need to determine if there was some type of vertical stretch or vertical shrink that was applied to that quadratic function. And we do that by finding some other point on the graph. Sometimes this is a y-intercept, sometimes it's an x-intercept, sometimes it's just some other random point. But you do need to make sure that it's one that you can see very clearly. All right, this one does have an y-intercept at 0, -2. We also have a corresponding point at -4, -2. Either one of those is fair game to use. I'm going to use 0, -2. That means when x is 0, y is -2. So I'm going to plug in -2 for my y and 0 for my x. And that will help me solve for a, because now it's the only unknown in that equation. That gives me -2 equals a times 0 plus 2, which is just 2, squared minus 8. So that's a times 4, which is just 4a minus 8. We're solving this equation. We'd add 8 to both sides. Gives me 6 equals 4a. Divide by 4 is 6 over 4, but that reduces to 3 over 2. So a is 3/2. I'm just going to plug this in up here. The function would look like y equals 3/2 x plus 2 squared minus 8. I now have all the missing pieces for that vertex form equation. One thing to note is that you do have to have y equals or f of x equals, some equals there for it to be a function. So we want to write y equals first. All right, the second graph, we can also find the vertex. It's sitting up here at 5, 6. And they gave you a point that's already kind of listed on the graph. So we're going to use that vertex first. That's our hk of vertex form. So y equals a times x minus 5 squared plus 6. We can already see that is a quadratic function shifted right 5 up 6, which is how we got to that vertex. But we need to figure out what the vertical stretch or shrink is, and I'm going to use this point 1, -4. If I'm using 1, -4, that means when x is 1, y is -4. And we'll simplify this and solve for a. So -4 equals a times 1 minus 5 is -4 squared plus 6. That's -4 equals, so -4 squared, 16, 16a plus 6. And we're going to subtract 6. Subtracting 6 gives me -10. And divide by 16. That's negative 10 over 16, but you want to reduce that fraction. So negative 10 over 16 gives you a decimal. We can find the fraction. It's negative 5/8. And then we just convert this to vertex form, or write this in vertex form. So y equals negative 5/8 x minus 5 squared plus 6. There's our vertex form equation. If we needed it in standard form, we could just expand this out. It would not be as pretty because we do have a fraction in this one, but it would still be possible. You have one more graph. This one we cannot find the vertex very easily, but we can identify the x-intercept. So I can see kind of where the vertex is. Maybe it's somewhere like halfway, but I don't want to estimate a vertex. I want to know exactly where it is. But since we know the x-intercepts are at negative 5 and positive 2, we can use our factored form. Earlier we had used factored form to find the x-intercepts, and we could set each factor equal to 0. So when we had something like x plus 7 times x minus 10, something like that, you could set each factor equal to 0 and then solve and get your two x-intercepts. So this one would have been at negative 7 and 10. All right. We're going to use that same idea. To get an x-intercept at negative 5, we're going to work backwards. This one we had originally set equal to 0, so I'm going to move that value back over. In this case, I'm going to move the 5 back over, and it's x plus 5 equals 0. So now one of the factors would be x plus 5. We also had x equals 2 as one of the x-intercepts, so I can do x minus 2 equals 0, shifting that 2 to the left side. So another factor is x minus 2. Just like before, we still don't know if there was a vertical stretch or vertical shrink, so we're going to put a placeholder and then plug in a point. Now we can't use the x-intercepts because we've already used them to create the factors. So we need some other point on this graph. Luckily, we do have one, like the y-intercept. So 0, 8. You could pick another point. There's one at negative 3, 8. But I'm going to use 0, 8. That means that y is 8 when x is 0. I'm just going to color code this for us a little bit. And solve it out there. So you can see I've plugged in the y-intercept, and now we're solving for a. This would be 8 equals a times 5 times negative 2. 5 times negative 2 is negative 10. Negative 10 times a is just negative 10a. And dividing would give me negative 4/5. You're dividing by 10, that's 8 over negative 10, which does reduce to negative 4/5. So our function in factored form would say negative 4/5 x plus 5 x minus 2. It doesn't matter what form it's in, each form has its own advantages. So having something in factored form is helpful when you're finding the x-intercepts. Having in standard form can be helpful for finding the x-intercepts if you're using the quadratic formula. Vertex form is always nice to help find the vertex. Lastly, we're going to write the equation given specific roots. So if we have a quadratic equation whose roots, x-intercepts, are negative 6 and negative 5, negative 6 and negative 5, but has a leading coefficient of 3. In this case, since the roots were negative 6 and negative 5, we do this similarly to what we did previously in the last example. We know an x-intercept is -6 and -5, so I can set them equal to 0 by moving the 6 over, adding it to the other side. I can move the 5 over, add it to the other side, and they're both equal to 0. Those are the two factors that we would have used for the zero product property. This function also stated that the leading coefficient would be 3. So that is going to make this 3 in front. That's helpful, but we do need to think about if you were to distribute this out, this would have been an x times x, which is x squared. And so x times 5 would be 5x, 6 times x would be 6x, so 5x and 6x makes 11x. And 6 times 5 is 30. With that 3 hanging out there, if I distribute it, it becomes y equals 3x squared plus 33x plus 90. Notice that the leading coefficient is 3, so we do have an accurate representation of this quadratic. In this last one, we have a quadratic whose roots are 3/4 and -2. So this one's a little trickier because we have a fraction in this. The fraction came because we had to divide both sides by 4, so we're going to undo that by multiplying both sides by 4, which makes that 4x equals 3. And then subtracting the 3 over gives me 4x minus 3 equals 0. There's one of the factors that we can use. We had another x-intercept at -2. If I add the 2 over, that gives me x plus 2 equals 0. These are our two factors for that quadratic function. So I'm going to rewrite that as 4x minus 3 times x plus 2. But the leading coefficient is supposed to be 8. Now, I knew in that last one that it had to be a 3 there, but this one's honestly a trick question a little bit. This is not supposed to be an 8. So we're going to leave that as it's unknown. And as you work with these more, you'll figure out why that's going to be an unknown value for right now. But let's distribute this out. That would be a 4x squared. 4x times 2 is going to be 8x minus 3x minus 6. So this would have distributed out to be 4x squared plus 5x minus 6. And if I distribute the a, whatever number that was, that's going to impact our leading coefficient. We're supposed to have a leading coefficient of 8. In that case, to get this leading coefficient for the x squared term to be 8, I find that a needs to be 2. If that was a 2, then that'd be multiplied by the 4x squared, and it would give me the 8x squared that we need. So you could write it in standard form like this, or you can leave it in factored form. That a just needs to be a 2. Both of those are equivalent, so neither one is more right than the other.